Okay, so before we got cut off, we were about to try to solve for, oh, I wanted to actually solve you to solve this time for an index of refraction. So as we were being cut off, I had said, let's say we're going from air to water. If we do that, then you'll know both of the ends and you won't have to solve for the index of refraction. Okay, so let's instead say we're going from to air to something else, and we don't know what the something else is. So the index for air, when you look it up, 1.00029. The angle of incidence we said was 30 degrees. I want you to actually solve for the index of refraction, and so let's say the angle is 20 degrees. Okay, so again, you write Snell's law. N1 sine theta 1 is equal to N2 sine theta 2, and this time you're solving for N2. Okay, so you're going to divide both sides by sine theta 2. So it'll be N2 is equal to N1 sine theta 1 over sine theta 2. Now I know this is going to be hard to imagine, but sometimes when we get to this point, I have a student who wants to cancel out the signs. You can't do that, right? This sign's attached to this theta 1, this sign's attached to this theta 2. You cannot just cancel the signs and have N1 theta 1 over theta 2 and think it's going to work out to be right. Okay, so no canceling of the signs. Instead, we're going to put our air in 0, 0, 0. Might be a fourth zero. I might have one too few zeros there than I'm supposed to. But you still get the same idea of how to do it. Just use the right index. Over the sine of 30 divided by the sine of 20. Okay? And so then you punch this in your calculator. And while you're doing that, I'm going to check the index. It really is 3 zeros, so I'm okay. And so we punch it in our calculator. 1.00029 times the sine of 30, which is 0.5, divided by the sine of 20, which is a nastier number, and you get an index of refraction, N2, to be 1.462. Okay? Bigger than the index of air, which means this was going from air into something more dense. Okay? And I didn't find an index on purpose to look like for you to see if it was a substance that we know. But if you were to look on the chart, I don't have the book with me, but the one in the one in your notes, there's not really anything close to it. But there would be something in the book because that chart is bigger. So you could look it up and you could say, oh, this must be whatever. Okay, so that's how you do the questions. There's just one other little thing I want you to think about that I want to talk about, and then you can go and do all the different questions, hopefully without too much problem. And that one little thing is, sometimes when you're going from more dense to less dense, something really cool can happen. So imagine I'm coming in at some angle, theta 1. And if I'm going from more dense to less dense, MLA, it's going to bend away. So instead of coming straight through, it's going to bend up like this. But then what's going to happen if I make my theta 1 even bigger? If my theta 1 is even bigger than it was, then it's going to bend up more. And if I make it bigger again, it's going to bend up more. And you should be able to imagine that there will be some theta 1, some angle of incidence where the refracted ray will go right along the surface. When that happens, what you found is the critical angle for this particular substance. And we usually call this theta C. And the critical angle is when the angle that theta 1 is equal to, which causes theta 2 to be 90 degrees. Okay, so By definition, the critical angle is the angle of incidence which makes the angle of refraction 90 degrees. And something really cool then happens in Snell's law. So we have n1 sine theta 1 is equal to n2 sine theta 2. And if this becomes the critical angle, you could change this to c. That means this becomes the sine of 90. And if you check on your calculator, the sine of 90 is just equal to 1. So then what you're left with is n1 sine theta c is equal to n2. So the equation for critical angle is sine theta c is equal to n2 divided by n1. It's really just a special situation of Snell's law. That special situation is you're finding the angle that makes the angle of refraction equal 90 degrees, which causes this whole side of the term sine theta 2 to go to 1. So you can find the critical angle for a material. Thing is, it's only going to happen when you're going from more dense to less dense. It will never happen when you're going from less dense to more dense, because when you're going from less dense to more dense, the refracted ray bends towards the normal. No matter what the angle of incidence is, you will never get the refracted ray to go along the surface. Okay, so critical angle only works when you go from more to less. When you're doing questions, if it doesn't tell you the second medium, or if it doesn't tell you, in Snell's law, if it doesn't mention one medium and it only tells you what the second one is, and for critical angle, if it doesn't tell you what the second medium is that's less dense, it's always air. So if it says find the critical angle for water, it means it's going from water to air. Back in the Snell's law questions, if it says a ray of light strikes the surface of water or the surface of a glass and it doesn't mention what it's coming from, that will be air. Okay, in this guy though, remember critical angle, the second one will always be air because it has to be going into less dense. Okay, something else cool happens though. What if I make my angle of incidence bigger than my critical angle? So what if instead of it being at the critical angle, the angle of incidence is really all the way down here? Then what's going to happen to the ray that should be refracting? Well, what happens is if it keeps moving up, and it's going to end up coming up here. It's going to get reflected back into the same medium. It won't refract at all. Instead, it'll get reflected, and that's something that's called total internal reflection. Okay, total meaning all of the light that strikes the surface, all of it. None of it's going to pass through. It's all going to reflect off, internal, back into the medium that it came from. And then reflection, it's coming up. Okay? This property then means that the light doesn't actually leave the medium. It goes back inside. And this will only happen if you're going from more dense to less dense and your angle of incidence is greater than the critical angle. We use this principle in something called fiber optics. Fiber optics are tiny little glass tubes. Now, they're really tiny. You might see them sometimes in Christmas decorations where they're really small. And we use it to pass light along. So we shine light in at an angle bigger than the critical angle. It gets reflected off, and then it keeps reflecting all the way along without losing any of the signal. It travels at the speed of light, but this is what like high-speed internet and stuff uses. Okay, and the signal is really strong because it's traveling at because it isn't losing anything, and it's really fast because it's traveling at the speed of light. Okay, so you can now do all the sets of questions right up to the end in your notes, down to the end of critical angle. Okay, if you have any issues, please post them in the group and then I can answer them. I might be tied up in the next couple of days because